The nearest star to our own is so far away that our fastest spacecraft would take around 70,000 years to reach it. And according to Einstein, there is no shortcut. The speed of light is a wall you cannot cross. Except that hidden inside Einstein's own equations, there seems to be a loophole, a way to cross that distance without ever breaking the speed of light. For decades it was dismissed as impossible, until a handful of recent discoveries started to suggest otherwise. To understand why crossing to another star is so hard, you first have to get a sense of the distance involved. The closest star to us, after our own sun, is a small, faint red dwarf called Proxima Centauri. It sits in the direction of the constellation Centaurus, in the southern sky, quietly burning at a fraction of our sun's brightness, so dim, in fact, that you cannot see it with the naked eye at all, despite it being our nearest stellar neighbor. It lies a little over 4 light-years away. Written out in ordinary units, that distance is about 25 trillion miles, or 40 trillion kilometers. Let us just pause on that figure for a moment. 25 trillion, that is a 2, then a 5, and then 12 zeros, trailing off behind them. It is the kind of number you can say out loud in a second and never truly picture, and that is not a failing on your part. Our brains were shaped to judge the distance across a field or a valley, not the gulf between suns. This is exactly why astronomers stopped using miles and kilometers for the stars long ago and switched to the light year instead. A light year is not a measure of time, as it sounds, but of distance. It is simply how far light travels in a single year, moving at its incredible speed the whole way. 1 light year works out to roughly 9.5 trillion kilometers, or about 6 trillion miles. It is a unit built for a universe too big for ordinary numbers. And when even a unit designed for cosmic distances still leaves us with figures in the trillions to reach the nearest star, you start to appreciate what we are truly up against. So instead of trying to feel the number directly, let us measure it against the fastest thing that exists, light itself. Light travels at around 300,000 kilometers, or 186,000 miles, every single second. That speed is almost impossible to overstate. In the time it takes you to draw one slow breath, a beam of light could travel all the way around the Earth more than 7 times. Snap your fingers, and in that instant light could cross an entire continent and come most of the way back. Nothing in the universe moves faster than this. No object, no signal, no whisper of information has ever been found that can beat it. It is the universe's built-in speed limit, and as far as everything we have ever measured can tell, it is absolute. Now hold that speed in your mind and consider this. Even light, the fastest thing in all of existence, takes 4 years and 3 months to travel from Proxima Centauri to us. Not 4 hours, not 4 days, more than 4 years, moving at 300,000 kilometers every second the entire way. And that fact carries a strange and rather beautiful consequence. The light landing in your eyes from that star right now actually left its surface more than 4 years ago. When you look at Proxima Centauri, you are not seeing it as it is now. You are seeing a portrait of it from the past, a message that has been traveling towards you since before you can quite remember. If it had flared or dimmed a year ago, you would have no way of knowing yet. The news is still on its way. That is the challenge in a single image. And here is the part that really lands. Proxima is the easy one. It is the closest star there is, the friendly one right next door. Sirius, the brightest star in our night sky, is more than twice as far. Betelgeuse, the great red star in the shoulder of Orion, is so distant that its light takes centuries to reach us. Every other star in the sky is further than Proxima, and many of them are hundreds or thousands of times further still. If 4 light-years already feels beyond reach, the rest of the galaxy is a distance the human mind genuinely cannot hold. There is one more way to feel the size of this gap, and it is perhaps the most humbling of all. Our entire Milky Way galaxy is around 100,000 light-years across. Proxima Centauri, our nearest neighbor, sits just over 4 light-years away. So if you shrank the whole galaxy down until it fitted on a map the size of a continent, the distance to the very closest star would still be a journey in its own right, and everything else, the hundreds of billions of other stars, would lie further out across that vast map. We have never sent anything even a fraction of the way to the nearest one. The furthest we have reached is still, in cosmic terms, barely a single step beyond our own front door. A tinken. So the real question was never whether the stars are far away. They are almost unimaginably far. The real question is how close we have actually come with the technology we have today to making a journey like that. Because it is one thing to know that the stars are far, it is another to measure that distance against our own best efforts and see just how enormous the gap really is. And if that is the kind of question you like to sit with, the deep, quiet, how far can we really go, then a subscribe means you will be here for the rest of the answer. Because to find out how close we have come, we can look at the fastest object human beings have ever launched, which is out there in the dark right now. That object is Voyager 1, and its story is worth knowing because it represents the absolute limit of what we have so far managed. It launched from Cape Canaveral in Florida in September of 1977, a spacecraft not much bigger than a small car, carrying instruments less powerful than the phone in your pocket. It flew past Jupiter and Saturn, sending home images that reshaped how we saw the outer solar system, and then it just kept going, out into the dark. After nearly 50 years of continuous flight, it is now the most distant human-made object in existence, further from home than anything our species has ever sent. In August of 2012, Voyager 1 crossed an invisible frontier called the heliopause, the boundary where the stream of particles flowing out from our sun finally gives way to the thin gas that drifts between the stars. In that moment, it became the first object built by human hands to leave the sun's bubble and enter true interstellar space. As of 2026, it sits about 16 billion miles from home, which is roughly 26 billion kilometers, and it is still whispering a faint signal back to us across that emptiness, a signal that now takes almost a full day to reach the antennas on Earth. In fact, around early 2027, it will pass a remarkable milestone, becoming the first thing we have ever made to sit a full light day away from us. That is how far this little machine has traveled, and there is something quietly moving about it. Voyager 1 was built with the technology of the 1970s, launched by people, many of whom are no longer alive, and yet it is still out there, faithfully sending back its faint signal from the edge of everything we know. It is the furthest reach of human hands, drifting silently through the dark, and even it has barely begun the journey to another star. And Voyager is not slow. It moves at about 38,000 miles an hour, which is close to 17 kilometers every second. To put that next to things we understand, a passenger jet cruises at around 600 miles an hour. A high-powered rifle sends its bullet out at roughly 2,000. Voyager is moving something like 19 times faster than that bullet, without ever pausing, without ever slowing down. At that pace, it covers hundreds of millions of miles every single year. By any human standard, it is blisteringly, almost incomprehensibly fast. But now, we do the piece of arithmetic that quietly breaks the heart. Take that blistering speed, turn Voyager towards Proxima Centauri, and work out how long the trip would take. The answer is around 70,000 years. Let that settle for a second. The first true cities of human civilization were built roughly 5,000 years ago. Writing, agriculture, everything we think of as history fits inside that window. Voyager's journey to the nearest star would take more than 10 times the whole span of recorded history. Whole civilizations would rise and fall and be forgotten before it ever arrived. And once again, this is the nearest star. Point Voyager at Sirius instead, and the travel time climbs past 150,000 years. Aim for a distant giant like Betelgeuse, and the spacecraft would fail long before it ever got close. So the obvious response is the one everyone reaches for. If the ship is too slow, build a faster one. And it is here that we run into something far deeper than an engineering problem. There is a trap built into the very way rockets work, and no amount of cleverness with ordinary fuel can escape it. A rocket moves by carrying fuel and throwing it out the back at high speed. The push of that exhaust drives the craft forward. But fuel has weight, so if you want to go faster, you need to carry more fuel. And that extra fuel also has weight, which means you need still more fuel just to push it along, and then more again to push that. Each addition makes the problem worse. The numbers do not grow gently and evenly. They spiral upward and explode. Physicists have a name for this vicious circle. They call it the tyranny of the rocket equation. To see how brutal it is, think about the Saturn V, the enormous rocket that carried the Apollo astronauts to the moon, still one of the most powerful machines ever built. Its first stage alone burned through around 3,000 tons of fuel in about 2.5 minutes, and all of that furious effort was spent simply to lift a small capsule with 3 people to our nearest neighbor in space, the moon. Now try to scale that up to a star, which is not thousands of miles away, but tens of trillions. To reach Proxima within a single human lifetime, using ordinary chemical rockets, the amount of fuel you would need is greater than the entire planet could supply. You could drain every oil well and strip every resource on Earth, and the equation would still refuse. Brute force, quite simply, does not get us to the stars. This is the point that so often gets lost in dreams of space travel. The barrier between us and the stars is not really a matter of building a bigger engine or a bolder rocket. We could pour the entire wealth and industry of the planet into a single chemical rocket, and it would still not carry a crew to even the nearest star in anything less than tens of thousands of years. The limit is written into the mathematics of how rockets work, and no amount of ambition rewrites mathematics. If we are ever going to cross these distances, the answer cannot come from pushing harder. It has to come from somewhere stranger. If raw power is a dead end, then perhaps ingenuity is the way through. And for the better part of 70 years, some of the sharpest minds in science have tried exactly that, designing engines that sound like they were pulled straight from science fiction. Each one is a genuine leap of imagination, and each one, as we are about to see, runs headlong into the very same ceiling. The first serious idea was almost unbelievable, and it came surprisingly early. In the 1950s, a group of engineers proposed a spacecraft called Project Orion, and its method of propulsion sounds like something a mischievous child would invent. The ship would fly by dropping atomic bombs out of the back, one after another, and riding the shockwave of each explosion forward. A thick metal plate at the rear would absorb each blast and pass the push on to the craft. As alarming as that sounds, the physics genuinely worked on paper, and the payoff was extraordinary. A design like this could in principle reach a few % of the speed of light. That is fast enough to make the crossing to Proxima in perhaps a century or two, rather than 70,000 years. But the drawbacks were just as extraordinary. You would be launching a vehicle powered by a long string of nuclear detonations from the surface of the very planet you live on, with all the radiation and political danger that implies. Unsurprisingly, Orion never left the drawing board, and yet, for all its madness, it remains one of the few designs ever proposed that could genuinely have reached another star with technology we already possessed. That is the strange tension running through this whole chapter of the story. The ideas that could actually work are the ones we dare not build, and the ideas we could safely build are the ones that are far too slow. Then there is fusion, the same reaction that powers the sun itself, forcing light atoms together so that they merge and release a tremendous burst of energy. A fusion-powered rocket would be clean, efficient, and capable of sustaining thrust for a very long time, and it remains one of the most genuinely promising long-term ideas for reaching the stars. The catch is a stubborn one. We have not yet managed to build a fusion reactor that reliably produces more energy than we pour into it, even in a laboratory bolted to the ground, let alone a version light and compact enough to fly aboard a spacecraft. The engineering is improving, but a working fusion starship is, realistically, still many decades away. More extreme still is antimatter. For every ordinary particle, there exists a mirror image partner made of antimatter, and when the two meet, they do not simply collide, they annihilate one another completely, converting every last scrap of their mass directly into energy. That makes it the most concentrated fuel the laws of physics allow. A tiny amount would release staggering power. The problem is not the physics, but the supply. Antimatter barely exists in nature, and the amount we can manufacture in our largest particle accelerators is almost unimaginably small. Producing just a single gram of it with today's technology would take far longer than the journey it was meant to fuel, at a cost that beggars belief. And even if you had it, storing something that destroys itself the instant it touches ordinary matter is a problem no one has solved. The most realistic of all the ideas may be the one that carries no fuel whatsoever, the light sail. Instead of an engine, the craft would unfurl an enormous, mirror-thin sheet and a powerful array of lasers back on Earth, would shine on it, the gentle but relentless push of the light itself driving the sail forward, much as wind fills the sail of a boat. A serious research effort called Breakthrough Starshot has studied this in real detail, aiming for around a fifth of the speed of light, which could carry a probe to Proxima in roughly 20 years rather than centuries. That is genuinely within sight, but there is a heavy condition attached. The idea only works for a featherweight probe, something on the scale of a computer chip trailing a sail behind it. To push a ship large enough to carry human beings, the sail would need to be miles across, and the laser array would have to draw a significant fraction of all the electricity generated on Earth. It is worth pausing to appreciate just how far these ideas already stretch what is possible. These are not lazy proposals. Some of the finest engineers and physicists of the last century poured their careers into them, and each design squeezes real, hard science for every drop of speed it can give. Orion would harness the most violent energy humanity has ever unleashed. Fusion would tame the very reaction that lights the stars. Antimatter would convert matter itself into pure energy, the ultimate expression of Einstein's famous equation, and the light sail would ride nothing heavier than a beam of light. Between them, they represent the outer limit of what pushing through space can achieve, and every single one still falls agonizingly short of a nearby star within a human lifetime. So we are left with an uncomfortable conclusion. It is not that we lack the imagination, or the engineering skill, or the will. It is that the target itself is defended by the laws of physics. As long as we insist on traveling through space, the speed of light stands over every design like a wall none of them can climb, which forces a strange and rather wonderful question. What if the answer is not to climb the wall at all, but to change the ground we are standing on? Look across all of these ideas together, and a pattern quietly emerges. Each one is brilliant. Each one takes real physics and pushes it to the very edge of what is possible. And yet not a single one of them can break through the final barrier, the speed of light. However clever the engine, the speed limit still stands. But there is something else they share, an assumption so natural that we barely notice we are making it. Every one of these designs tries to push harder, to move faster, through space. And what almost no one thought to question was whether the real mistake was hiding in that one small word, through. To find the loophole, we have to stop treating the speed of light as a vague slogan and look closely at what the rule actually says. In 1905, in his theory of special relativity, Einstein showed that anything with mass can never quite reach the speed of light. The reason is subtle and rather elegant. The closer an object gets to that speed, the harder it becomes to push it any faster. It behaves as though it is getting heavier and heavier, resisting every extra shove. At 99% of the speed of light, a spacecraft would effectively weigh several times what it does at rest. Push closer still, and the effect runs away from you. To actually touch the speed of light, you would need an infinite amount of energy, and infinite energy does not exist anywhere in the universe. So for any object at all, a person, a starship, a single grain of dust, the speed of light is a wall that can be approached but never, ever crossed. You can get closer and closer to it, spending more and more energy for less and less gain. But the final step, the one that would take you to light speed itself, always demands more than the entire universe could ever provide. It is not a wall we have failed to break through for lack of trying. It is a wall built into the deepest logic of reality. But now read that rule again, very carefully, because the exact wording matters far more than it first appears. Nothing can move through space faster than light. Through space. The rule is about objects traveling across space. It says nothing at all about space itself. And this is precisely where Einstein's other great theory, general relativity, quietly opens a door. In that theory, space is not a fixed, empty, unchanging stage on which events play out. It is something flexible and almost fabric-like. It can bend around heavy objects, it can be stretched, and it can be squeezed. And here is the crucial part. There is no speed limit whatsoever on how fast space itself is allowed to stretch or shrink. Now, this could sound like a convenient bit of hand-waving, so it is worth stressing that this is not just a clever argument on paper. We can actually see it happening, right now, across the sky. The universe is expanding, and the most distant galaxies we can observe are receding from us so quickly that the space between us and them is growing faster than light could ever travel across it. That sounds like a flat contradiction of everything we just said, until you look closer. Those galaxies are not racing through space at impossible speeds. In their own local patch of the universe, they are barely moving at all. It is the space in between us that is stretching, swelling in every direction at once, carrying those galaxies further away as it grows. The simplest way to picture it is to draw two dots on a rubber band and then pull the ends apart. The two dots drift away from each other, yet neither dot actually crawls along the surface of the band. Neither one moves, in the local sense. It is the material between them that has grown, pushing them apart without either of them taking a single step. Space behaves in exactly this way, and it can do it at any rate at all, because the speed limit that traps ordinary objects simply does not apply to the stretching of space itself. The rule was only ever about things moving through space. Space was never a thing moving through anything. And this is not some obscure technicality tucked away in a corner of theory. It describes the actual history of our universe. In the first fraction of a second after the Big Bang, cosmologists believe space underwent a burst of expansion so violent that distant regions were driven apart far faster than any beam of light could have crossed the gap between them. Nothing broke the rules, because nothing was traveling through space. It was space itself, unfurling. That same principle, the one that shaped the entire cosmos in its opening moment, is the loophole we are now trying to exploit on a much smaller and more deliberate scale. Now, a careful mind will already be raising an objection here, and it deserves an honest answer. Are these just tricks of appearance? When something looks as though it is moving faster than light, is anything real actually happening, or is it all illusion? And the honest answer is that yes. In most cases, what we are seeing is what physicists call apparent motion. The thing that appears to break the speed limit is a pattern, or a shape, or a shifting point of view, not a solid object, and not a message being carried from one place to another. This distinction is the heart of the whole matter, so it is worth stating plainly. In every single case that has ever been examined, no actual object and no piece of information has ever outrun light through space. That rule has never once been broken, and there is no sign that it ever will be. The loophole was never about beating the rule. It is about the quiet, astonishing fact that space itself was never bound by that rule in the first place. Which leaves us standing in front of a genuinely tantalizing thought. If space can stretch and shrink without any limit, then in principle, you would not need to move faster than light to cross the galaxy at all. You would simply need to persuade space to do the moving for you, to shrink the distance ahead and expand it behind. For a long time, that was pure speculation, an idea whispered at the edges of physics. But there are real signs, both in the laboratory and out among the stars, that the universe genuinely does allow geometry to outrun light. And the clearest of those signs arrived only very recently. Everything we have said so far about space bending and stretching has been theory, elegant theory, backed by solid equations, but theory. So it is fair to ask whether the universe ever really lets something outrun light in practice. And in early 2026, in a laboratory small enough to fit in an ordinary room, we got our clearest answer yet. The experiment was published in the journal Nature by a team working across the Technion, MIT, and Stanford. What they were studying was light, but not the bright part of it. They were studying the dark part, and to see why light even has a dark part, we need one simple idea. Light travels as a wave, and when a wave of light gets twisted and folded in the right way, there are certain points where the wave completely cancels itself out. At those exact spots, there is no light, just a tiny point of darkness, sitting right in the middle of the glow. Scientists call these points optical singularities, but you can just think of them as little holes of shadow, embedded inside a beam of light like the still center of a whirlpool. For decades, these dark points were known only in theory, because catching them in the act is fiendishly difficult. They are unimaginably small, and they appear and vanish in mere quadrillionths of a second. To even have a chance, the team used a clever trick. Rather than watch light racing through empty space, they sent it into an ultra-thin flake of a special crystal, where the light slows down to around 1/100th of its normal speed, dragging along with the material as it goes. Slowing the light down was like switching from a blurred snapshot to a proper slow-motion film, and for the first time it let them actually watch the dark points move. To capture it, they used pulses of electrons fired in perfect time with the light, acting like the shutter of an impossibly fast camera. The whole setup is a small marvel of modern physics in its own right. The ability to film events that unfold in quadrillionths of a second is itself a recent and hard-won achievement, one that is now opening windows onto a world that was, until very recently, completely invisible to us. And when they looked at that footage, they saw something strange. When two of these dark points drifted together and canceled each other out, they did not simply fade away. They sped up, faster and faster, until, for a single fleeting instant, they crossed the speed of light. And this was not a one-off, not a stray measurement they could dismiss. Almost 1/3 of all the dark points they tracked did the very same thing, briefly slipping past the speed of light before winking out of existence. For an effect that had lived only in equations for half a century, that is an astonishing thing to catch on film. Now, your first reaction should be suspicion, because if a real object had crossed the speed of light, physics as we know it would be broken. So the important question is, what was actually moving? And the answer is the key to this whole story. Nothing physical was moving. A dark point is not an object. It has no weight. It carries no energy. and it carries no information. It is just a pattern, a spot where the light happens to cancel out. And a pattern can shift as fast as it likes, because there is nothing solid there to slow it down. The clearest way to see why this is allowed is with an example you can picture in a second. Say you shine a laser pointer at the surface of the moon, and then you give your wrist the smallest flick. The little dot of light on the moon would leap sideways across kilometers, across miles, in a heartbeat, far faster than any rocket could ever fly. And yet nothing actually made that journey. No physical object raced across the lunar surface at superhuman speed. The dot is simply the place where the light happens to be landing, and a place can move at absolutely any speed you like, because a place has no weight, no substance, nothing to hold it back. The dark points in that laboratory are the very same idea, turned inward and shrunk down small, and this experiment was the first time anyone had ever caught them on camera doing it. And this same effect is not confined to the lab. It shows up out among the stars, on the grandest scales imaginable. Astronomers have watched jets of matter blasted out by black holes that appear to move at several times the speed of light. Telescopes have seen rings of light seem to sweep across clouds of dust around long-dead exploded stars, racing outward far faster than light should be able to travel. Every single time, once the measurements are picked apart, it is the same story. What is moving so quickly is a pattern, or a reflection, or a shifting point of view, while nothing physical and no scrap of information actually beats the speed of light. There is a useful way physicists put this. The part of a wave that seems to break the rule, the crest that appears to surge ahead, carries nothing with it. The part that could actually carry a message, a signal, a piece of information, never crosses the line. The illusion can outrun light. The message never does. And what makes the laboratory result so satisfying is that it was predicted long ago. Back in 1974, two physicists named Michael Berry and John Nye worked out the mathematics of these dark spots in light and predicted that they should behave in exactly this way, even racing past the speed of light as they canceled out. For 50 years, it stayed nothing more than a line of equations on paper, because the effect was far too small and far too fast for any instrument to catch. It took a machine capable of slicing time into pieces just 3 femtoseconds long, 3 quadrillionths of a second, to finally freeze the motion and prove the two of them right, half a century after they first put pen to paper. So here is the pattern worth holding on to, because it is the whole key to what follows. Faster than light, without breaking the rule, it really is possible, but only as long as the thing that moves is not a solid object carrying mass and energy. It has to be a shape, a location, a feature of the geometry. The dark point in that laboratory is one example. The stretching of space itself is another, and that brings us to the real prize. If a person can never be pushed through space faster than light, but space itself is completely free to move without limit, then perhaps the answer was never to travel through space at all. Perhaps the trick is to make space carry us. And remarkably, back in the 1990s, one physicist worked out precisely what that would look like. His name was Miguel Alcubierre, a Mexican theoretical physicist who, in 1994, was still a young researcher and who freely admitted that he was a lifelong fan of Star Trek. He had grown up watching starships casually flick on their warp drives and leap between the stars, treating it as the pure fantasy that it was. But somewhere along the way, a real question lodged itself in his mind. He knew the mathematics of general relativity intimately, the very equations that describe how space bends and stretches, and he wondered whether, buried somewhere inside those equations, there might be a way to make that piece of fiction genuinely obey the laws of physics. So he framed the question as precisely as he could. What shape would space itself have to take so that a region of it could travel faster than light, while everything sitting inside that region never moved faster than light at all? The answer he found is now called the Alcubierre metric, and the picture it paints is genuinely beautiful. Picture a small bubble of space. Inside that bubble, everything is calm, flat, and completely ordinary. A ship resting in there would feel no motion and no force at all. No crushing acceleration, no sensation of speed. The clocks tick normally. Light behaves exactly as it always does, and to the crew, it would feel as though they were simply sitting still in ordinary space. Now look at the edges of the bubble. At the front, space is being squeezed and contracted, shrinking the distance to wherever the ship is headed. At the back, space is being stretched and expanded, pushing the bubble onward from behind. The ship itself never flies through space in the ordinary sense. It is carried along, cradled inside its calm pocket, by a traveling wave in the shape of space itself. The closest everyday comparison, and the one this idea is famous for, is a surfer riding a wave. A surfer is not swimming. They are standing still on their board, expending almost no effort, while the wave beneath them does all the moving, sweeping them forward at the speed of the water. In this design, the ship is the surfer, and the wave is a ripple in the fabric of space. To an observer watching from far outside, that bubble could sweep across the galaxy faster than light itself. But to the crew inside, nothing dramatic is happening at all. They are simply resting in a quiet, flat pocket of ordinary space, having broken no law of physics whatsoever. That is the quiet genius of it. Nobody inside ever goes faster than light. It is the space around them that carries the speed. There is a subtle beauty in what this would mean for the people on board. In every other scheme for fast travel, acceleration is the enemy. Push a ship hard enough to reach a useful speed, and the force would crush the crew against the back wall long before they got anywhere. But in a warp bubble, the ship never accelerates at all in the usual sense. It sits perfectly still inside its calm pocket, while the geometry does the work outside. The crew would feel nothing, no pressure, no sense of speed, no strain, even as the bubble carried them across light years. In principle, you could travel between the stars while feeling as though you had never left your armchair. Meanwhile, to anyone watching from outside the bubble, the ship would appear to streak across the heavens faster than any beam of light. Two completely different experiences of the same journey. Stillness on the inside, impossible speed on the outside, and neither one, remarkably, breaking a single law of physics. This is the strange, quiet magic that kept physicists coming back to Alcubierre's idea, even as the practical problems piled up. Alcubierre laid all of this out in a short paper, only 8 pages long, published in the journal Classical and Quantum Gravity in 1994, and it landed with real force in the world of physics, because he had done something almost nobody expected to be possible. He had taken the warp drive, a pure piece of television invention, and rewritten it in the rigorous language of Einstein's own equations. It was no longer just a fantasy. On paper, at least, it actually worked, and the paper went on to become one of the most cited theoretical physics papers of its decade. Suddenly, serious scientists were writing about warp drives in respectable journals, not as fantasy, but as a genuine solution to Einstein's equations that simply happened to describe faster-than-light travel. The idea had crossed a line of its own, from the realm of imagination into the realm of physics that could be studied, criticized, and refined. In the years that followed, the concept picked up a small but dedicated following among physicists willing to take it seriously. Some worked on the mathematics, hunting for ways to make the bubble more efficient. Others asked harder questions about whether it could ever be stable, whether it might damage whatever lay in its path, or whether the very act of switching it off could be dangerous. None of these questions had easy answers, and none of them have been fully answered even now. But the fact that thoughtful scientists were asking them at all marked a quiet shift. The warp drive had earned its place as a real problem, worth the effort of real minds. There was, of course, a catch, and it is worth being honest about it, because it is the part that often gets glossed over in the excitement. Even if you could somehow build such a bubble, steering the thing turns out to be a profound puzzle in its own right. The inside of the bubble is, in a very real sense, sealed off from the space outside it, which makes the ordinary business of sending a signal to speed up, slow down, or change course extraordinarily difficult. How would the crew even tell the bubble where to go? These are not minor engineering wrinkles to be ironed out later. They are deep, open questions that only the most recent research has begun to seriously explore. But even steering was not the greatest obstacle. The greatest obstacle was the sheer price the equations demanded simply to build the bubble in the first place. And for a very long time, that price looked so impossibly high that the whole idea seemed destined to stay locked on paper forever. To bend space the way the bubble requires, squeezing it tight at the front while stretching it open at the back, you need a very unusual ingredient. Think of how ordinary matter behaves. Any object with mass curves the space around it inward, the way a heavy ball pressed into a trampoline creates a dip that other things roll towards. That inward curve is exactly what we experience as gravity, but to make the rear of the warp bubble push outward rather than pull inward, you need the precise opposite, something that curves space the other way, that repels instead of attracts. Physicists call this negative energy, or exotic matter, and it would behave like a kind of anti-gravity. The difficulty is enormous. We have never held a usable quantity of the stuff. We have only ever glimpsed the faintest hints that it can exist at all, and it may simply not come in the form the bubble would need. And when Alcubierre first ran the numbers, the situation looked hopeless. The amount of this exotic matter his design demanded was truly staggering. Early estimates suggested you would need a quantity of negative energy comparable to the mass of the entire observable universe. All of it, just to move one small ship. The reason the figure was so absurd came down to the shape of his bubble. Its wall, the shell where space did all its bending, was incredibly thin and sharply curved, and that made it monstrously, ruinously inefficient. For years, that single number kept the warp drive firmly in the realm of a lovely mathematical dream, admired by physicists, but with no visible path to reality. Then, slowly, the numbers began to fall. In 1999, a Belgian physicist named Chris van den Broek found a clever way to reshape the bubble. His insight was to keep the room on the inside large enough to hold a ship, while shrinking the bubble's outer surface, the part facing the universe, down to something almost unimaginably tiny. By reworking the geometry this way, he slashed the requirement dramatically, bringing the cost down from the mass of the entire universe to something closer to just a few times the mass of our own sun. That is still far, far beyond anything we could gather. But it was no longer a preposterous, impossible figure. It was merely an extraordinarily hard one. And in physics, that shift, from impossible to merely very hard, is everything. The dream had taken its first real step towards the possible. Over the following 2 decades, others chipped away at the problem from new angles, testing whether different arrangements of matter and different bubble shapes might bring the cost down further or soften the need for exotic matter altogether. None of it produced a ready-to-build starship, and honest researchers were always careful to say so. But bit by bit, the warp drive stopped being treated as a joke at the edge of physics and started being treated as a serious, if extraordinarily difficult, question. The direction of travel was clear. Every few years, the impossible looked a little less impossible. And the most striking progress of all has come only very recently. In 2024, a team of physicists from the University of Alabama in Huntsville, working alongside a research group called Applied Physics, published a new study in Classical and Quantum Gravity, the very same journal that had carried Alcubierre's original paper 3 decades earlier. Using a purpose-built simulation tool they named Warp Factory, which let them model warp bubbles on a computer and test them against the laws of physics, they achieved something genuinely remarkable. They designed a working model of a warp bubble that needs no exotic matter and no negative energy at all, only ordinary, positive matter, arranged in exactly the right way. To grasp why that matters so much, remember the whole reason the warp drive had been stuck. The one ingredient it seemed to demand, negative energy, was the very thing we could not obtain and might never be able to. A design that sidesteps it entirely removes the single biggest roadblock that had stood in the way for 30 years. It does not solve everything, but it takes the most impossible seeming requirement off the table. There is a lesson in the careful way the researchers themselves talk about their work. They are not promising starships, and they are quick to correct anyone who says they are. What they have shown is narrower, and in a way more valuable. That the tools now exist to study these ideas properly, to test a proposed warp bubble against the full weight of Einstein's equations, and see exactly where it succeeds and where it breaks. That is how real progress in physics tends to happen. Not in a single triumphant leap, but in the slow, patient business of turning something impossible into something merely difficult, and then chipping away at the difficulty year after year. Now, it is important to stay clear-eyed here, because this is exactly the kind of result that gets wildly overstated the moment it leaves the laboratory. This design does not let you cross the galaxy faster than light. The version that removes the need for exotic matter is, for the time being, a slower-than-light bubble, a way of carrying something along inside a pocket of gently bent space, but at ordinary speeds. The faster-than-light version, the true warp drive of the imagination, still calls for forms of energy we do not yet know how to create. So let us be honest and plain about it. We are not on the verge of building a starship, and anyone who tells you otherwise is getting ahead of the science. But make no mistake, something real has changed. For the first time in the whole history of this idea, a warp drive is no longer just an equation scratched out on paper. It is a structure that can be modeled, tested, refined, and argued over on a computer, built entirely from physics we already understand. The central question has quietly shifted. For 30 years, the question was whether such a thing was even permitted by the universe at all. Now increasingly, the question is how far the design can be pushed, how much closer to the dream each new refinement can carry us, and that, after a century of the door being firmly shut, is a completely different kind of question to be asking. Think back to where we started, a distance so vast that our fastest ship would spend 70,000 years crossing it, and a speed limit that Einstein seemed to have bolted shut forever. For most of the last century, that was the end of the conversation. The stars were simply out of reach, and that was that. But the universe turned out to be subtler than the wall suggested. The rule was never that nothing can move faster than light. The rule was that nothing can be pushed through space faster than light, and space itself was never bound by it. A point of darkness in a laboratory can outrun light. The edge of the observable universe already does, and has done since the beginning of time. Neither one breaks a single law, because in both cases, what moves is a shape, a boundary, a piece of geometry, and not a solid thing carrying mass through space. And somewhere in that distinction lies a door that, for the first time in 100 years, is no longer firmly bolted shut. It is only ajar. But ajar is not the same as closed. Maybe that door never opens all the way. Maybe the exotic matter stays forever out of reach, and the warp bubble remains a shape we can draw but never build. And even if that turns out to be true, there is still something quietly remarkable in all of it. We are a species that learned to read the fine print of the universe's own laws, and found, folded deep in the mathematics, a hint that the road to the stars might not be forbidden after all, only very, very hard. And hard is a kind of problem we have faced down before. There was a time when crossing an ocean was the edge of the possible, and a time when leaving the ground at all was a dream that sober people dismissed. We have a long habit of standing in front of walls that everyone calls permanent and quietly finding the crack. Perhaps the stars are simply the next wall, and perhaps, somewhere in a paper only a few years old, in the shape of a bubble drawn on a computer, we have just seen the first thin line of light coming through it. If you want to keep pulling on that thread, the next piece of the puzzle is the strange, restless nature of empty space itself. The idea that a vacuum is never truly empty, and that the flickering energy hidden inside it might one day be the very thing that makes a bubble like this possible. That is where this story goes next.